Okay, then I'd like to welcome you all to the online session on smart water tools in wastewater treatment. Well, sorry for the delay. We have we had a few technical problems, but it seems that everything has been solved. Let me briefly introduce myself. My name is Hans Aalderink. I'm working at Deltares. Deltares is a knowledge institute in the field of water and subsoil, and I have a background in water quality and water quality modeling, but not so much in artificial intelligence and the small tools, the smart tools that you are going to present. Well, however, it's interesting to see how smart technology and artificial intelligence rapidly entered the water domain the last decade. Well, new sensor technology rapidly developed, and terabytes of data can be collected at reasonable cost nowadays. And this requires new technological developments to be used in research, but also in practice for finding solutions for well, emerging problems. Well, these technologies, such as the use of big data tools and artificial intelligence, they will be presented today. Well, typically these tools are used for, as far as I see, data interpretation, decision making, and process control. Well, in today's session, we have three examples. One is on the application in the field of water reuse in agriculture, and the two are on wastewater treatment. Well, I would like to ask you to use the Q&A button at the top right of the screen for putting your questions, and after each presentation, you have the opportunity to ask questions to the presenters. Well, the first presentation is made by Burcu Yazici. She is an environmental engineer and works as a water resource management specialist at the Turkish Water Institute for 9 years now, and her research area mainly focus on agriculture, water pollution, water quality management, and reuse. So I would like to invite Ms. Burcu to do her presentation. Ms. Burcu, the floor is yours.
Thank you very much, Mr. Aalderink, for the introduction, and thanks for including our study in the Amsterdam International Week. It's a pleasure to be a part of this prominent event. So my presentation is on smart tools for efficient water use and reuse in agriculture. And currently we are studying this topic as part of a PRIMA-funded project, which is called Waternet, and we are conducting a case study in Konya Close Basin on this issue. So let me start with the general characteristics of the basin. If we can move to the next slide, please. So Konya Close Basin lies in the middle of Turkey, and the agricultural areas cover nearly 60% of the basin. That said, the area has a semi-arid climate, and the water resources are quite scarce in the area. The surface water resources are mostly seasonal, therefore the water demand is mostly met from groundwater resources. And when you look at the crop pattern, the most widely grown crops are water-thirsty ones, such as sugar beets, sunflower, with all sorts of grains, fruits, and vegetables. So the main concern of the basin is the overuse of water resources due to intense agricultural activities. And as you can see on the right-hand side of your screen, around 95% of the water is used for agricultural purposes alone. So if we can move to the next slide, you can see here that the water demand of the basin is quite higher than the water potential of the basin, and this demand is expected to rise even further in the future with an increment in non-agricultural uses as well. So far, unsustainable irrigation methods and unlicensed wells led to a groundwater depletion of over 30 meters over the past decades, and this also resulted in the formation of sinkholes in the basin due to its karstic formation. So you can see one of the sinkholes as the background picture of the slide. we have around 600 sinkholes formed in the basin due to over-abstraction of water uses, groundwater use. And apart from these issues, climate change models also predict that 20 to 30% drop is expected in precipitation in the basin. So for these mentioned reasons, we have to urgently revisit our agricultural practices in the basin and also seriously take into account water reuse options in the basin. So that's what we are focusing on with Waternet project. And before I move further with our case study, I would like to also introduce you to our project a bit. If we can move to the next slide, please. Thank you. So Waternet is a PRIMA-funded project, and it started in 2019. And this project is led by University of Murcia from Spain, and we are in total 8 partners from 5 countries with the aim to develop a decision support system which is based on Internet of Things. And the idea is to manage the whole water cycle in agriculture, and we would like to achieve this by monitoring water resources and water demands online and log every agricultural data in a decision support system, and also include water governance, socio-economic factors as well to take a more integrative approach in agricultural production and water use efficiency in agriculture. So the decision support system, which we call the Waternet platform, is an open source interoperable platform composing of different layers. And the data acquisition layer gathers not only historical data on water resources availability and water demand and agricultural data, but it also collects data from smart tools such as weather stations, soil moisture sensors, piezometers, and it also processes satellite images as vision sensors to provide multispectral information into the platform. And as I just mentioned, the platform will also provide an ICT tool to evaluate socioeconomic aspects through analytical framework and indicators. And these will be based on the water governance principles of OECD. So we are currently conducting with Waternet 3 case studies in Algeria, Spain, and Turkey. And all of these case studies serve for optimizing water and fertilizer inputs in agriculture. So this will be one of the outputs of the platform, which meaning that the platform will provide fertilizer and irrigation plans for end users in the end. And in addition to optimization studies, our Algerian partners are also testing the potential of agrivoltaic systems in terms of energy production, the effect of shading on crops' irrigation needs, plants' tolerance to shading, as well as rainwater harvesting potential of the system. And in the Turkish case study, we are focusing on water reuse options. And now we can take a closer look at our case study in Konya. If we can move to the next slide. So in the Turkish case study, we are testing 2 of the most widely grown and most water-consuming plants in the basin, which are corn and sugar beet. And we are also considering the lack of presence of modern irrigation technologies in the area, because we know that for the most part, they are still using sprinklers for the production of sugar beet, at least. We deployed drip irrigation in the area. And of course, we are continuously monitoring weather and soil conditions through climate station and soil moisture sensors. And these devices are directly linked to the Waternet platform. And also we are carrying out, of course, water, soil, and plant quality analysis throughout the study. So these data will also be uploaded to the platform, and in the end, all of these data will serve us to develop irrigation and fertilization plans for different types of crop for producers. And this platform will also allow us to draw more bespoke irrigation and fertilization plans for water use options as well, because we will take into account the treated water quality parameters. And to sum up, we are almost ready to harvest our first term products from the field. And once we do that, we will be able to see how efficient the water and fertilizer management is in the area. And we will also see what are the gaps that need to be improved for the second term. So in the second term, we will be able to fine-tune the platform and produce accurate and sound fertilization and irrigation plans for the end users, hopefully. And in the end, the users will be able to access the platform through user-friendly interfaces. So a user will be able to enter his plot into the system, and once they enter certain agricultural production data to the system, they will be able to get irrigation and fertilization plans on a weekly or monthly basis. So this is the idea, but additionally, the platform will be able to produce certain alerts with regards to agricultural production and water use efficiency. So one example could be that the platform will be able to send comments to actuators so that they can control the water flow to and through the canals remotely. So this is also one of the options that the platform will serve in the end. And that's briefly our study. Thanks for your attention. And I think I will take your questions now. Thank you very much.
Thank you, Burcu, for your interesting presentation. And also for keeping on time. We have time for some questions. I see a first question in the Q&A from Jan-Peter van der Hoek. He says 95% water is used in agriculture, a deficit of 536 cubic hectometer. Can water reuse cover the deficit, or do you need additional sources?
There is currently a water transfer from another basin, and they are also thinking of water transfer from other basins to cover up the deficit. But we know that this is not a sustainable solution. So that's why we are mostly focused on reuse options for the basin, but also, of course, we need to think about the crop pattern in the basin as well. So these are the issues we need to tackle with in the future.
Okay, thank you. Another question from Huub Reinhardt. Do you also select for water efficient crops?
At the moment, we are not focusing on the crop pattern, as I mentioned. We are mostly focused on dealing with how to deal with water reuse options in the basin. But of course, this is one of the issues we need to further tackle in the upcoming years. We need to possibly change to more efficient, water efficient crops.
Okay, thank you. Any other questions? Well, as far as I understand, you used monitoring data and did an analysis of historical data to find the optimal schemes for irrigation and fertilizer use. You're making scenarios. That's what I understand from your presentation. Well, do you see any options in the future for real-time control of irrigation systems using these type of data? And how could, let's say, artificial intelligence be beneficial to that? Can you reflect on that? It's a dot on the horizon, maybe?
I'm not an expert of artificial intelligence as well. Our coordinators from Spain are the experts of this issue. But as far as I'm concerned, and as far as I have learned from my colleagues in the project, I think this is the way forward. So we must be learning to deal how to best cope with these artificial intelligence to manage water efficiency in agriculture, because what we have seen so far by field studies is that the farmers usually use their own knowledge to irrigate the crops. So they are not really into the science and technology part so much. They are a bit hesitant to use technology. So we must be learning how to really use artificial intelligence to get the most of it. And also we should be engaging more with end users in order for them to understand how to use it better, so that we can really save water and produce the same quality of crops by using less inputs. But I think, yes, we should be tackling this issue further for the future.
That's the next step in
Yes,
future.
I think so. Yeah.
probably the dot on the horizon. Okay, thank you. Well,
thank you very much.
Are there any other questions, please? There's time for one last question. I don't see any questions popping up in the Q&A. So then I thank you once again for your presentation and answering the questions. Then let's move on to the next presentation. Actually, the next two presentations are related. Both are on the wastewater treatment plant of Amsterdam West. And both are also, as far as I see, the result of an European-funded Horizon 2020 project, showing good cooperation between European partners. The first presentation is made by Dr. Alex van der Helm. He works as a consultant water technology at the Research and Consultancy Department of Waternet. And he is a project manager, and he advises on drinking water treatment technology and IT and water research and innovation. And he also is leading, and that's interesting, the Waternet Data Lab, a data science team that implements artificial intelligence solutions in the operations of Waternet. Well, the title of his presentation is Artificial Intelligence for Wastewater Treatment, the development of a digital twin used to train a control optimization agent. Please, Mr. van der Helm, go ahead.
Yeah, good morning, everyone. And Hans, thank you for the introduction. Alex van der Helm, I said, can we move to the next slide? Because we already seen the title. I work for Waternet. It's the water cycle utility of Amsterdam. And we do all wastewater drinking water in Amsterdam and surrounding areas. Next slide, please. So we do this for about 18 municipalities and about 1.3 million inhabitants. Next slide. And I want to present to you a work we did on a wastewater treatment, smart water apps using AI. And it's part of a Fireware for Water project from Horizon 2020. And in this, I won't elaborate on this. Siddharth's session this morning elaborated a bit on this project, but I want to highlight that there are 4 demo cases. There's one in Greece, one in France, one in the UK, and one in Netherlands. And the one in the Netherlands, next slide, that is led by Waternet here in Amsterdam, and it's about our wastewater treatment plant Amsterdam West. Next slide, please. So this is our wastewater treatment plant Amsterdam West. It is a 1.1 population equivalent treatment plant, which treats all the wastewater of the city of Amsterdam. And one thing that I want to point out in this picture is that if you don't look at the 3 tanks in the front, but the tanks thereafter, they are covered. And that's good to know because they are covered, we can measure all the off gas of these tanks. And normally, most of the times, these tanks are open. Next slide, please. Well, and because they are covered, and my colleague Marcel Zandvoort started about 5 years ago with a real-time measurement of nitrous oxide. Up till then, we knew we had these emissions, and there were rules of thumbs for it and estimations, but we really want to know what exactly is the emission. And it's important because it's a potent greenhouse gas, nitrous oxide. So what we did is for over 5 years already measured it in real time, and we found that about it changes per year, but it's 15 to 28 kiloton per year CO2 equivalent. And you can, it's large because it amounts to approximately half of our total climate footprint as a water utility. So it's really relevant, and we wanted to do something about this. So next slide. So what we did is one of the 7 treatment lanes of Amsterdam West, we dedicated it as a research lane, and we added additional sensors within this research lane, and also we wanted to see if we can optimize the control with a lowering of nitrous oxide and electricity use of our aeration. With discussions from experts in the field, we discussed about white box modeling, gray box modeling, black box modeling, as artificial intelligence is, and we're heading now within this part on the AI part, and also KWR is working on the biowind part, which, as I said, session talked about a bit this morning. So next slide. So what kind of online sensors are we talking about? Well, here you see that we have built a research facility at the site of the treatment plant, where we added, for instance, sensors to really well measure the nitrogen in the influent. We have made an ultrafiltration skid so we can measure as well dissolved nitrogen as total nitrogen, and the same for organic carbon, total organic carbon and dissolved organic carbon in real time. We added in the aeration tank a number of extra sensors. And also in the off gas, of course, I already told you, there we have the nitrous oxide measurement. Next slide. So here, this is a picture of the AI setup we have been working on so far. So we have a lot of real-time sensor data from existing sensors that are already there at the plant, and from the newly installed sensors within this project. And from the sensor data, we derived several soft sensors. So these are not physical sensors, but we have built models to generate certain data that we need for the modeling. For instance, we have an influent soft sensor. We measure the total influent of the treatment plant, but we don't measure how many water per treatment enters per treatment lane. So we built a soft sensor that estimates the amount of water for every separate treatment lane. Very important to know the load of an aeration tank. Also, we do an influent forecast of the coming 40 hour and 15 minutes based on rain meters, and also on a measured influent flow. And all these data we use to build a digital twin, and we call this the environment model. It's a digital twin of our treatment plant that not only contains water quality data, but it also includes data from set points, data from certain valves, whether they're open or closed in the aeration system for the process air. And this digital twin is used to train an optimization agent you see on the right. And the optimization agent will be discussed a bit more by Lluis Echeverria, who will present after me, so I won't go into detail about that. But the idea is that we will optimize the amount of energy used and the N2O emission. So next slide, please. So here you, for the data scientists among us, you can see what kind of models we used. Now, for instance, for the influent soft sensor, it's a quite simple rule-based model. But for some of the soft sensors, we use multi-layer dense neural networks or LSTM models for the influent forecast. And the digital twin itself is a recurrent neural network. Next slide, please. So what is then used as an overview for this data in the digital twin? I said that the set points, it's the oxygen set point in the aeration tank is the main point, and it's also the set point that we are optimizing as a first step for the control agent. Water flows, also internal recirculation flows within the aeration tank. Water quality parameters, as I said, oxygen, ammonia, etc. The air flows of the incoming process air, and of course we also measure the off-gas flows, also the amount, the normal cubic meter per hours, water quality parameters of the off-gas, the blower data we use, the energy use, and I set air force settings. Next slide, please. But before we can use this data, we have an anomaly detection and correction on this data, because data is not always correct. So therefore we use some statistical methods. We use also the interquartile range method to detect spikes within the data. And we have some, we detect physical outliers. For instance, the oxygen concentration will never be below 0. So that's not very complicated, but it's good to do up front. We have flatline detection, and this is also work that KWR is doing some more in-depth research on. So the next slide. Here you see some results of the validation. So we have a data set of about 5 months. We don't have a data set yet that contains a whole year, so it's a bit difficult to already take in account all of the seasonal aspects within this. But we have found that 3 to 4 months has a sweet spot in training of the model. And here you see some results of the nitrous oxide, which is quite well to be described by our models. But when you want to optimize the control, we will give the model different control settings that it hasn't seen before. So it is interesting how the model reacts if we do a prediction on prediction for multiple days. And in the next slide, you can see this is still work in progress, that we are quite able to do predictions on predictions with the model for a couple of days, and to test the different control settings with this. If we go to the next slide, then you see that we're aiming at implementation. So also if you see the soft sensors we built, they are already implemented in our systems. We do this step by step. So they're running continuously, and operators and our technologists can look at the data generated by our soft sensors. And here you see that in our process automation, we have made some adaptations so we can include the modeled derived set points within our treatment plant. We already did some tests with fairly simple models, and next step is to introduce one of the new ones that we are developing at the moment. And it's quite unique if you think that we are running these models in our Azure environment in Dockers, and we are actually able to control the whole treatment plant in a very safe and secure way. So last slide. So what are the lessons learned? Well, installing and maintenance of new sensors is really time consuming. It takes a lot of attention for constantly checking the data quality, but it already gave a lot of new insights in the processes with having all this new additional information we didn't have before. We put extra eyes in the processes. We do this in an agile way, and we learn quick. And we fail quick, and that really helps you in implementing these new technologies. So we have a real close interaction. It is necessary between the data scientists and the technologists, and you really need, for a project like this, as well data scientists, but also machine learning engineers. So the machine learning engineer is the guy who can make sure that the model runs continuously, that it's fits within the architecture of your utility, that if it fails to send some data, that it automatically starts again, that you can do automated tests on it. So, and that's not really the work of a data scientist, but it's essential if you want to implement an AI solution. And also, well, as last, I think we just started to explore the power of implementation of AI. It's work in progress. We have learned really a lot already. And I'm really looking forward to all the coming work of the different research institutes and utilities in the coming years. So next slide. Thank you for your attention.
Thank you, Mr. Alexander Helm. Thank you for your interesting presentation. Well, we have time for questions, and I saw a first question in the Q&A by Jan-Peter van der Hoek. He's referring to one of your sheets that showing the N2O emission, and well, mentioned of notices that it varies a lot over the year. And his question is, can you explain that by the digital twin or even improve the operation of the wastewater treatment plant to reduce emissions?
Yeah, it's a good question. We cannot yet explain it by the digital twin. And the reason for that is that we don't have a data set that covers all the data we need for such a long period. This is just the N2O emission, so we don't have for instance, the nitrogen load at that time, or some other data we are actually measuring. We are measuring right now, but we are building up this data set maybe now for the past 8 months. So I hope we will be able to do in the future, but it will take us probably another year, 2 years to have data sets that can run multiple years. Yeah.
So you need longer time series.
Yeah. To be able to well predict also the yearly changes in this. Yeah.
Okay, thank you. Any other questions? Time for a few more questions. Well, you optimized on energy use, or that's the goal, on energy use and N2O emissions.
Yeah.
How about treatment and efficiency? Is that also included? Because, well, the goal of this treatment plant is...
Of course, yeah. It's a good question, but of course we have as a boundary conditions that we remove what we need to remove, of course. So it's within the boundary conditions that we have, try to optimize to this goal. Yeah, good question. Yeah.
Okay, thank you. Any other questions? Well, then I have a more general question to you, Mr. van der Helm. You are heading the Waternet data lab, and well, you presented an application on artificial intelligence on wastewater treatment plants. Could you briefly tell something on the other fields where Waternet is using artificial intelligence in their operations? Just please keep it brief, but it's just
I can quickly give a few examples. One other example that's totally different from this in the wastewater treatment plant is, for instance, we send our customers, for instance, tax invoices for their water taxes, and what we do is we estimate with a model based on about 20 million data points we already have, what the chances are that people will object to them. And that's very important for the load of our people that have to work on this, that have to answer all these objections. So we predict them, and they can say, okay, then we need this amount of people for this period to work on this and answer those. But we also, for instance, for drinking water, we did with 30 students of the University of Amsterdam. We made predictions of the coming years of the drinking water usage, and then based on additional features that up till now we cannot use, or we did not use, to see if we can better estimate what our yearly production should be. And we can use that again, for example, for our budget estimates, etc. So those are a few examples of which we work on as a team. Yeah, so it can be quite diverse, but we try to focus more and more and see where the greatest value can be for our colleagues. And well, these are some examples of it. Yeah.
Okay. Well, thank you. Well, it's interesting to see how these, let's say, smart technologies and AI is finding its way to practice already at a company as Waternet. Well, thank you. Okay, thank you for your presentation and answering the questions. We will move on to the last presentation that is made by Lluis Echeverria. He is an advanced researcher of the Applied Artificial Intelligence Unit at the Eurecat Technology Center. And he's also a collaborator of ESADE and the Mediterranean Agronomic Institute of Zaragoza, and part-time lecturer at the Department of Computing Engineering, Computing Science and Artificial Intelligence area at the University Autónoma at Barcelona. And he presently is working on a PhD in this field. And his presentation is also on the, which was also mentioned by the previous speaker, also on the treatment plant of Amsterdam West. And he will speak about the AI agent-based service for optimal control. So please, Mr. Echeverria, the floor is yours, and please start your presentation.
Thank you, Hans. Thank you for the introduction, and good morning, everyone. Thank you for letting me be there presenting our work, which is called Artificial Intelligence for Wastewater Treatment and Artificial Intelligence-Based Service for Optimal Control, which is the result of a close collaboration between Waternet and Eurecat under the Fiber for Water project in the Amsterdam demo case introduced by Alex in the previous session. Next slide, please. Yeah, next one. Thank you. Yeah, the objective of the research is the design and implementation of an advanced service based on different methodologies and algorithms from data science, data mining, artificial intelligence, or machine learning domains to provide real-time advice or real-time decisions for an optimal wastewater treatment plant control. The target is one of the main key processes carried out in the Amsterdam Wastewater Treatment Plant West, the activated sludge process, and more specifically, the aeration stage. An optimal control of this process will directly end up with an improved effluent water quality and operational cost reductions, and also directly and indirectly with a reduction of greenhouse gas emissions. This schema has been already introduced in the previous session, where Alex explained the implementation of the digital twin, the left part of this diagram. Now I'm going to share the main details about the right part, the optimal control agent. Next slide, please. Yeah, here we propose the use of reinforcement learning algorithms for the implementation of this optimization and control tool. Reinforcement learning is a specific technique from the machine learning domain focused at developing agents for optimal and autonomous control. These algorithms are based on a computational approach to understand and automate goal-driven learning and decision-making, which combined with recent advances in deep learning or in deep neural networks, using them as a policy system, this engine becomes a powerful tool to operate and manage large, high-dimensional and complex environments, such as the one we are dealing with, the wastewater treatment plant. So the result of this combination of this algorithm with these methodologies is known as deep reinforcement learning. How it works? The idea is quite simple. The agent, with no prior knowledge, continually interacts with the environment. As you can imagine, that the training environment corresponds to the wastewater treatment plant digital twin presented by Alex. And then the agent learns which are the most optimal actions given a specific state in order to optimize the long-term signal, or a long-term signal called reward. Next slide. Yeah, first, we formalize the problem as a continuous Markov decision process with the following 4-tuple state action spaces, reward function, and discount factor. The state entity was designed to accomplish the Markov property. The Markov property says that the future is independent of the past given the present. It means that the agent must have all the needed information in the current state in order to pick the correct action or to select the correct decision. To do so, we modeled the state with the following information: the current wastewater treatment plan status, defined by 17 parameters, the ones that we have, that we see here, plus the previous whole day of information, same variables, with 15 minutes time steps. So 96 past observation plus the current status ends with 96 observation forming the state. This data will be used by the agent to understand and identify the wastewater treatment plan dynamics. Additionally to this information, we also provide the agents with the forecast of the input flow, which will help the agent to adapt and prevent future situations. Two different ways are implemented for the action space, but both deal with the O2 set point to control the aeration stage. I'm going to comment on this in the following slides, and the reward signal is based on cost minimization. I am also going to comment on this. Additionally, there is another important parameter, the discount factor, which controls how important are future rewards at the present moment. We are still working on this value. Next slide. Yeah, regarding the two approaches to implement the action spaces represent what kind of actions the agent can take. The first approach defines a discrete space where a specific number of actions are available. Currently, we are working with 3 actions. Action 0, increase the previous set point by 0.05. Action 1, decrease by the same amount. And action 2, do nothing. So keep the previous O2 set point. This is the current design, but we can decide to add more actions with different values for increase or decrease. On the other side, on the right side, the second approach does not limit the agent actions, and this is allowed to pick any valid value for the O2 set point. This way corresponds to the actual wastewater treatment plant operation model. We will see which approach ends with better results. Next slide. Regarding the reward function, currently it is based on N2O emissions and energy consumption. If only one of those variables were selected, the system will not learn how to balance this trade-off. We were discussing it in the previous session. So in order to provide an aggregated reward signal, the two variables are combined into a single goal. First, they are translated to CO2 equivalent, and later to cost in euros. Thus, the goal of the agent is to minimize the mid and long-term aggregated cost by maximizing a negative reward. This is what it is shown in this diagram. Next slide. Yeah, we are working with deep learning algorithm to solve the first approach with the discrete action space. Similar research used this algorithm and obtained good results. So this is why we want to try with it. The difference now is that we are implementing a recurrent deep neural network policy to process the temporal data, those one-day information. This is a logical diagram of the policy network. On the bottom, the input layer with 96 time steps, information from the whole day, followed by 2 LSTM layers, long short-term memory layers, the specific neural network layers to process the time series data, and followed by 2 fully connected layers to process the resulting values. The latest layer is the output and corresponds to the 3 q-values, one for each action, representing the expected long-term reward for each decision. 0 increase the previous set point, 1, reduce the previous set point, and 2, keep the same set point as in the previous time step. Next slide. We have not started with the implementation of the second approach with the continuous action space, but probably we'll use an actor-critic reinforcement learning algorithm. Actor-critic methodologies are one of the most recent advances in deep reinforcement learning, the deep reinforcement learning domain. Here we plan to test different algorithms which are based on completely different behaviors and can provide very different results, but we have not started yet on this experimentation. Next slide. Also, additionally to this experiment design, we also want to take advantage of what we did and what we have until now to try to speed up and simplify the agent training phase. To do so, we propose the use of 2 mechanisms from machine learning domain. The first one is known as transfer learning. The idea behind of it is to use the wastewater treatment plant digital twin, the predictive model, to provide a kind of baseline knowledge to the agents. Due to the digital twin is already trained and was implemented through a recurrent neural network, we can extract the bottom layers of this deep neural network. In this case, the recurrent layers, those layers that process the temporal data, and put them directly to the agent's policy neural network. So what we are doing is transferring this knowledge from the digital twin to the agent, so thus simplifying the training and reducing the computational times. These layers will not be modified. Next slide. Yeah, in a similar way, we also want to take advantage from historical data sets. We can assume that the wastewater treatment plant was optimally managed by the operators. So we can use this information to run a first training execution where agents will be provided with the operation decisions, with the real operation decision. Again, this will simplify the training and will reduce the computational time. Next slide, please. Finally, to conclude the presentation, I would like to mention which are our next steps. Currently, we are working on the second experimentation phase where we are training the agents. Some months ago, during the first training executions, we identified an issue in the digital twin long-term predictions, and we have been working on it until now. So now it's working much better. The next step will cover the hyperparameter tuning. Each algorithm, each reinforcement learning, or each machine learning algorithm has its own specific internal parameters, which manages how these algorithms work. So we have to identify which are the best for each scenario. This is a very complex process since there are a lot of parameters, and the training time goes from few hours to weeks, and depending on the algorithm and the size of the problem. Next, we plan to benchmark the next point in the next steps. We plan to benchmark the agents against different non-experienced situations, so we can analyze their reactions and decisions. And finally, the system integration. The resulting agents will be deployed and integrated into the Waternet legacy systems, as Alex explained it in the previous presentation. And yeah, that's all. Thank you for your attention and for questions.
Thank you, Lluis, for your presentation. A very technical presentation. Well, the floor is open for questions. Please, your questions in the Q&A. We still have some time for a few questions. Yeah, Jan-Peter van der Hoek has a question again. Input is 70 parameters. How selected? Expert knowledge. I don't see COD or BOD, which affects energy consumption.
Yes, but maybe Alex can provide better insight than me. But yeah, of course, we use their domain knowledge to decide which parameters we use for the agent's training.
Yeah, maybe I can add this. With 17 parameters, you also it's good to know that some of these parameters are combined from several measurements. So it actually is more than 20, 30 sensors, I think. But in some sensor values are combined to one parameter. And it's true that you don't see organic carbon in there yet, and that's because we have only been measuring TOC and DOC real time for a couple of months, and we're still having some issues with data. So what we are doing, starting with the measurements we have, and in an agile way, we want to improve step by step. Yeah.
Okay. I assume that answers Jan Peter's question. Any other questions? Let's wait a few seconds to see if one pops up. If not, then, well, I have, let's say, a more general question maybe to all presenters. What you see is that these technologies rapidly are implemented now, and well, I was just wondering, for example, looking at the wastewater treatment plant of Amsterdam West, but also this also probably refers to irrigation. How long will it take before the full wastewater treatment plant of Amsterdam will be controlled by artificial intelligence, and what are the main challenges? Let's say in sensor technology, in AI tools, but also in acceptance by the operators and managers. And that also refers to maybe to irrigation, to farmers, the acceptance to farmers. Maybe all of you could reflect on that in well, let's say a few sentences.
I can start. It's I think we're only just at the start of it at this moment. We're doing this in a separate treatment lane. So I think that we have the possibility to be able to do this already in a full-scale setting is already a really nice start. Still, we don't have any guarantees yet for how good it will work. So it will be very exciting in the coming months. And as I said, if you do it step by step, then you can also take technologists, plant managers, etc., with you. But well, we have the support of our technologists at the treatment plant, and I think that's the first step. But when it's fully controlled, well, that's I cannot answer that question.
No. Well, that's of course.
What I think is really important is that that you really try to implement it as soon as possible with very simple parts. So because once you do that, you will run into so much dependencies with, for instance, IT, your IT departments. We have a team cloud. We need to we work a lot with, and you have your infrastructure of your data infrastructure and connections, and it's all. If you build everything and then at the latest, and then if you say, okay, we're now ready, let's implement, then I think it will take you at that point enormous amount of time to really see the result of what you did. So with trying imperfect solutions already to implement, you make steps on the whole chain. On the whole chain you will eventually need if you want to reach a goal like this. Yeah.
So full implement. Well, you say, well, implementation is, let's say, just learning by doing.
Yeah.
And trial and error. Just
yeah,
do it.
Well, not totally trial and error. It's not all trial, but it's learning by doing. Yeah, that's
Okay.
I would formulate it like that. And I can tell you, we have already run and into a lot of obstacles and overcome a lot of obstacles. And well, it's I think we really learned a lot, but it's not easy. Yeah.
Okay.
But I think we need to, if you don't do it, you will never reach it. So just do it. Yeah.
Okay. Thanks. Burcu, could you reflect on that? Let's say from an irrigation perspective, farmers' perspective. How about acceptance by farmers of these technologies?
Of course, I agree with Mr. van der Helm. I think, yes, we are still learning by doing, but there are a lot of projects going on this matter. So I think we will be advancing quite soon in artificial intelligence and using it for water management in many sectors. That said, well, I have mentioned that farmers are a bit hesitant using technology for farming because they really do not trust much the technology. So we have to show them that the technology is working, and we are trying to do so by showcasing our results from the project. But I think here the technology leaders should work hand in hand with the governance leaders as well. So we should be doing this with scientists and local authorities and farmers all together. So stakeholder engagement is a must in here in order to success in using artificial intelligence in water management issues and in supplying and ensuring water efficiency in agriculture.
Okay, thank you. Well, still a lot of work to do, also on getting the acceptance by the end users, and in particular if you look at irrigation. Lluis, for you got the last opportunity to say something. How do you are an expert on IE? How do you see the let's say IE in the water domain? What will we reach the next, let's say, 5 to 10 years?
Yeah, we are actually involved in the several research projects, not only focused on wastewater treatment, but focused on all the water domain stages. So yes, I think and I hope that we will see very soon a very big jump on this area, and very, very important advances will end up due to the artificial intelligence implementation. Yeah.
Okay. Well, thank you. We're at the end of the session. I'm not going to summarize. I all gave you the opportunity to see or to say something on let's say the future. I also have great expectations of these new technologies in the domain of water. Like I mentioned at the start of this conference, it's of this session. It's interesting to see how these technologies already entered the last decade and how things are moving fast. And I'm really anxious to know how the water world will look, let's say, over 5 or 10 years. And we might have wastewater treatment plants and other plants that are fully controlled and running autonomous, like the cars are almost doing. So there's a big future in this. I like to thank all the presenters for their excellent presentations and also the discussion, and also like to thank the participants who joined this session. And thank you once again. Thank you. And if you follow other sessions at the Amsterdam International Water Week, please have fun. Thank you. Bye-bye.
Thank
you.
And on top of that, also thank you, Hans, for moderating this session. And thanks again to all the speakers.
You're welcome. Thank you. Bye-bye.
Bye-bye.
Thank you. Goodbye.